This was a really dumb idea. But you know, they put a lot of thought and work into this, which I find wonderful. They were going to shoot 0.1 kiloton of weapons every half second into this chamber. So the whole idea was they'd be blowing up. The big problem with this is they were going to be blowing up the bombs inside the ship. So Project Helios, which was Lord's Liverpool National Laboratory, worked on a similar design. Project Helios, and it used the same idea as the Martin design. And very soon these people realized that this was just dumb and they should stop, because normal people could realize that a 130-foot diameter rocket that blew up nuclear weapons in this was good. So instead, someone brilliant like Ulam said, you know what, this is silly. And he looked back at the Castle Bravo shot, those spheres, said, you know what? The thermonuclear weapon didn't explode inside of those little metal spheres, you know? It blew up outside of them, and it still propelled them. So why don't we just blow the bombs up outside the ship? And thus, nuclear pulse propulsion, as we know it, was born. In 1955, William and Cornelius Everett proposed a pusher plate and fuel disk solution. And what this was is they'd shoot a bomb out, then they'd shoot a disk of fuel, like a blade of propellant, and the bomb would go off, it would vaporize the propellant and shoot it at the ship. And so the propellant would hit the pusher plate would absorb the momentum of the propellant, and the momentum of the propellant would end up shooting the ship forward. This idea underwent a little bit of a revolution, and they decided, let's just stick the propellant in the bomb. And in 1958, General Dynamics actually decided to go somewhere with this, and they employed Freeman Dyson to work on the project. Another man who ended up being very instrumental in this was Taylor. He was in charge of he did a lot of work with the shaped explosives in the Manhattan Project, which, as some of you may know, are necessary for actually compressing the uranium in the implosion design of a bomb. So basically, the idea behind are you all familiar with the working principle of a nuclear weapon? Okay, so basically, those of you who don't know, all you basically have are a bunch of little atoms, okay, and they're unstable, okay, and when they're unstable, they end up undergoing beta decay. Well, in a bunch of other cases, and they end up little pieces of them come flying off, and one of the most important pieces that come flying off of unstable uranium nuclei are neutrons. And these neutrons, the important thing about these neutrons is they're not influenced by the electric fields of the electron clouds of the other atoms. So they're basically like these perfect little bullets, and they can come flying in and smash into other atoms, and cause fission to occur, splitting apart the atoms by shooting it with a neutron. And the rate of fission, of course, is proportional to the number of atoms you have crammed into a given area. So the trick was, well, we're going to take a nice big hunk of uranium, and it's going to be kind of larger in volume. So the actual fission reactions will be undergone at a safe and normal rate. But if we take explosives now, we compress it to an incredibly small size, then this will be happening at an extremely high rate, and then it goes so high that it ends up exploding and killing everyone. So that was what Taylor did. And then he was like, well, we're going to need shaped explosives for this, so why don't I take over your project here? And what's very interesting about this whole movement was that this was something that was completely independent of what NASA was doing at the time. And it would have caused, and so NASA at this time was working on these delicate chemical rockets that could carry small payloads and had to be built. They could not be very heavy, and they just weren't that ambitious. But the entire principle of a nuclear rocket would have been building this thing as strong as possible and as heavy as possible, because there was really not much of a limit to how much thrust you could put on, that you could tack onto this thing. I mean, you'll see how big they could possibly get in a few minutes. But this was a completely different method for designing rockets. These things would have been built like ocean liners, basically. Ocean liner tanks, that is. So the heavier the better, and thrust is not a problem, as opposed to chemical rockets. And Dyson was a little bit ambitious. Our motto was Mars by 1965, Saturn by 1970. And in principle, this entire project really would have worked. The original design was also equally ambitious. It called for a crew of 150 astronauts. The rocket would have been 135 feet in diameter. It would have shot out 2,000 bombs. When they were going through the atmosphere, they thought, let's be modest and not completely destroy the Earth. And shoot one out at 1 per second. But once we're clear of the atmosphere, no one's going to care. So we'll shoot out 20 per second for cruise speed. They had a whole 12-year plan. The budget, actually, the projected budget was not that expensive. The projected budget with adjustments was actually much less than Apollo. I think the figure that he gave was literally in the millions, and then they and the actual convert and it ended up, and if you had made it a 10-fold increase, it still would have been less than the Apollo program. One of the reasons for this, I think, was because we just had bombs lying around. So one problem so the beginning of the end note for the entire project was in 1959, when NASA decided that the entire civilian space program would be completely non-nuclear. And this was in part to appease public fears about nuclear technology. And another part was because they were actually making strides with chemical designs. At this point, I'm pretty sure that we've launched. Well, first of all, the Russians had shown already in 1957 that chemical rockets were working. They were actually launching satellites. I'm not sure when the Vanguard satellite was launched, but it was making strides here, and most of the NASA people were all obviously in favor of chemical rockets. So it became the predominant. It became the sole mission of NASA. So this project found itself without a budget, and the Air Force in turn decided, okay, we can fund this, but only if we can contrive military value from it. So they decided. So then they came up with this idea of sticking nuclear weapons on the thing, which actually makes sense to me, at least because this was a ship that was designed to go long distances and not just like stick stuff into orbit. But anyways, at that point, this vision of men of goodwill was abandoned, and yeah, 1.5 million was the actual project cost, and that was with adjustments for today's dollars. But it was finally all killed in 1963 when the atmospheric test ban treaty was signed, and so then basically. If the project, and then it was basically catch-22 because the project was militarily funded, and there was a complete ban on atmospheric testing of weapons unless some purely civilian use can be demonstrated. But since the military was in charge of it, they couldn't get funding for it, and it died off. Oh yeah, so there's some design considerations now. So now I'm just going to basically romp through the actual design documents. These are all available. These were all declassified back in the 90s, I think, so I welcome all of you to look through them. There's some really great pictures listed and shown here. But the design issues for this thing basically were you need to protect the crew. That's the big design issue.
Only the 150
You have to keep the forces on them within 1 to 3 Gs. And there's obviously the radiation danger. And then there was also the actual performance issues, which aren't as exciting. So now we're going to run through the design documents. So this here is actually a graph of the accelerator. So what the actual mechanism for both providing propulsion and for protecting the crew was the pusher plate apparatus. And the job of the pusher plate was to take, when the stuff hits the pusher plate, it accelerates the pusher plate at 50,000 Gs. The crew is attached to the pusher plate. The crew wants to be feeling 3 Gs. And it has to be feeling under 20 Gs if it wants to survive. How do you do this? So instead of this isn't going to tell you anything. The picture says it. All right. So basically, the essential design for this was you had the first stage of this. So it had 2